if you have a chemical reaction that has different phases, solid, liquid, gas, or aqueous? Then what we call that is a heterogeneous equilibrium. Hetero means different. So in this reaction, you can see that this is a gas, and then a solid. Okay, so in this reaction, you see the solid clump of carbon in the bottom. You can see the CO gas. This is the C, this is the O, the red is the O. You can see the CO2 here. Okay, so as you can see that the CO becomes CO2 and C. Okay, so the concentration of the C here, the molarity of the C, will not ever change. But the concentration of the gas, let's say the amount of molecules per certain volume will change. Here, the amount of atoms per certain volume will not change. Okay, I'm going to prove to you that the concentration of solids and liquids are constant. It does not change. Let's start with water. Water has a specific density. That means how compact each water molecule is conformed within each 1 milliliter. Okay, and if you weighed that matter, it'll weigh 1 gram. And that will never ever change. That's a property of water at a certain temperature, of course. Okay, so let's find the molarity. Okay, so 1.00 grams per milliliter. I'm not going to write the 1. Get the molarity. This is water. Molarity is equal to moles per liter, mole of water for every liter of water. So I'm just going to change this grams to moles. 18.02 grams. Water is 1 mole of water. Cancels, and now you're done with the moles. Okay, now the liters. We have 1,000 milliliters to 1 liter. The milliliter cancels. Do that math. Okay, pause the video, do the math. Okay, I got 55.5. And that's the same as 55.5 molar. So I have proven that water's concentration is always going to be 55.5 since the density is constant. It's a property of that matter. The same with a solid. If we have a piece of aluminum chunk, the atoms at that 1 centimeter cubed of volume weighs 2.70 grams. And that's a property of aluminum. That's how they're compacted in there. If I change that to molarity the same way as I did here, go ahead and pause the video and do it yourself. Okay, so I'm going to do 2.70 grams of aluminum per 1 centimeter cubed. Okay, again, change aluminums to moles. 1 gram of aluminum. I'm sorry, 1 mole of aluminum to moles is 26.98. Okay, so grams is gone. I'm going to bring centimeter cubed on top. 1 centimeter cube is the same as 1 milliliter. They're equal to each other, and centimeter cube's gone. 1,000 milliliters to 1 liter. 2.7 divided by 26.98 times 1,000. 100 point, if I wanted 3 sig figs. Moles per liter or molar. 100 molar of aluminum. So that is constant as well. I have proven to you that the concentrations are constant. Okay, since they're constant, that means they're not changing. Okay, so that means that it does not do not change in the equilibrium expression. So over here, if you were to write the equilibrium expression for this solution right here, this reaction right here, the equilibrium expression is equal to products CO2 times CaO over CaCO3. CaCO3. Okay, as you notice, this is a solid. That means this number is a constant number. Okay, this is also a solid. That means this number is also constant. CO2 is a gas. That number can change. If you compact the gas molecules, it'll be more dense, more molarity, and so on. Okay? So since these two, again, this K equilibrium is also a constant. So what we do is we take all the constants, this and this, combine them together, and you're going to get one big constant called K equilibrium. Okay? One big constant is just equal to CO2. That's the only thing changing. Okay? Therefore, if you're writing equilibrium expressions, do not include the solids, okay? And the liquids as well. Now, does that mean you don't need them in the reaction? Of course you need them. Otherwise, how are you going to make CO2? From what? From nothing? Okay, so this is what it looks like. Here's the CaO solid. Looks like a white powder. And here's the CaCO3 solid. Okay, and here's the amount of CO2. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, as long as you have some in there, look at this one, it has a lot more than this one, who cares? They're the same concentration. So as long as you have some in the container, you'll have 9 CO2s. But you have to have some CaCO3 as well. You have to have both. I don't care how much. You'll get the same amount of CO2 because it is the K equal to K equilibrium. Okay, so here's some practice. It says write the equilibrium expression Kc for the following reactions. Okay, so K equilibrium for A, K equilibrium is equal to products over reactants. Now for the products, CO. Do you write the liquid? No, you don't. Okay, over CO2 and H2. Okay, that's the equilibrium expression. Now let's do B. K equilibrium is equal to, do you write the 10? No, you don't. You write the CO2? Yes, you do. CO2 squared over, you don't write the solid either, but you write the gas. CO2. So to summarize, don't write solids and liquids because their concentrations don't change. Okay, so here's a problem. Go ahead and read it and try to do it yourself. Okay, so I hope that you tried that yourself first. So the reaction is CaCO3 solid turning into these two products. So here's the reaction up here. CaCO3 turning into CO2 and CaO. So in the first scenario, it says that you have pure CaCO3 in there. Will the reaction attain equilibrium? Well, look at the reaction. CaCO3 will break down into these two. Well, of course, you have the reactant that you need. So yes, it'll stop until you have 9 CO2s or a certain amount of CO2 that is at equilibrium. Okay? Yes, this will happen. CaCO3 will decompose, two products will form until CO2 pressure is at equilibrium or no longer changing. Pause the video and try B. Okay, it says CaO and CO2. You have CaO in there, and you have CO2 pressure greater than the value for Kp. So you have CaO and CO2. So you have some of this inside it, and you have CO2, and you have more than you need. Oh, yeah, you have some of that, so it's going to go backwards. It says you have pressure greater. Therefore, you have too much of this, too much CO2. Then, of course, it's going to go backwards until it'll combine with the CaO solid until you have just the right amount that's supposed to be at equilibrium. So, yes, it will go backwards until CO2 pressure is at equilibrium. Okay, number 3, or letter C. Some CaCO3 and a CO2 pressure greater than the value for Kp. So here, you have some of this, check, and you have too much of this. If you have too much, you're not at equilibrium, so it's going to want to go to the left. But to go, and you don't have any of this. To go to the left, you will need some of this, but you don't have any. So nothing will happen. You can't go to equilibrium. okay? Because you can't go backwards, you don't have any CaO. Okay, let's try D. You have CaCO3 and CaO. You have this and this. Sure, it'll go to the right. I don't care if I have that until I have just the right amount of CO2. It'll go to the right until CO2 is produced at equilibrium. So yes.